All right, today we have three more slides left in the logic gate design using pull up and pull down resistors and voltage control switches. All right, so let's go to our class notebook and we can wrap up this chapter. All right, we had stopped here last class. Any questions? Does everybody understand how we can design logic gates using simple switches and pull up, pull down resistors? Okay. All right, so next up is designing a 2-input NAND gate using 2 of the CD4066 switches and a pull-up resistor. So both these switches are connected in series, and if they're connected in series, they are providing a pathway to ground for our output terminal, which means both of them need to be on in order for the output to be connected to the ground. If either one of them is open, meaning the switch is off, then the output terminal is connected to the plus 10 volt line via the pull up resistor, right? So let's draw up the case scenario where VA is equal to 0 and VB is 1. And then when VB is 0 and VA is 1. So this is my output. And my VB is logic 1. And VA is logic low. One in this case, in terms of circuits and electronics, we are working with 0 and 10 volts. So VA 0 means we are applying 0 volts to it. VB equal to 1, meaning we are applying 10 volts to it. And then the other case where VB is 0 and VA is 1. Okay. And our output is still connected to plus 10 volts. Right. So these are the two case scenarios right here in the middle. Okay. And obviously, if both inputs, if both inputs are low, both switches are open, that means output is connected to plus 10 volts. So output stays high when either one of these inputs is open. The switch is open. And the only possible time that output can go low is if both switches are on. When both switches are on, V out is connected to ground via the two switches, and the two switches will have a on resistance. And so this indicates the on resistance of both switches. Okay. Since both are in series, R on plus R on. Let's take a pause. Let me know if you have any questions. Any questions? Oh. Do the steps make sense? Right. So faced with any circuit, we should be able to analyze based on the condition of the switches. We simply draw out the connections based on whether the switch is on or off. And then look where the output is connected, positive or connected to ground. Okay. When both switches are on, you have the resistance on resistance of both switches, which we can look up from the data sheet. So in the data sheet, if you're using a 10-volt system, then the on resistance is between 200 and 400, or 180 and 400. Right? So here they take about 500. Let's assume the highest according to the data sheet, which is 400. So it's 800 divided by 10,800. It forms a voltage divider network with the 10 kilo ohm resistor. And because it's following a voltage divider network, we simply apply voltage division, and we can determine the voltage at the output. In CPE 133 or E133, you're learning about digital design, where you simply learn that NAND gates, logic 0, 0 gives you a logic high, 0, 1 gives you 1, 1, 0 also gives you 1, and then 1, 1 gives you a 0. In terms of voltages and currents, there is some amount of current flowing through, and voltage, not quite 0. It's actually quite high, 0.9 volts, almost 1 volt. Okay, almost 1 volt. So as computer engineers, we are looking behind the curtain, seeing how the circuits work and see how circuits can be implemented, right? We can learn about binary number systems all we want, digital systems all we want, but behind digital systems, actual circuits, right? So somebody's got to build these actual circuits. Steps make sense, right? Okay, all right. Elementary 2-input gate. We'll figure this out together. I'm not leaving you by yourselves, okay? So you have 2 switches, now they're in parallel. What happens? Well, we see output is connected to a pull-up via a pull-up resistor to +10, right? Similar to the other one, but now instead of 2 switches in series, we now have 2 switches in parallel, which means the output will be connected to 0 through either one of them. So even if one of the 2 at a minimum is activated, then your output goes low, right? So if VB is 1, your output is 1. If VA is 1, I'm not 1, output is 0. If VA is 1, output is 0. And of course, if both are 1, then output is still 0. Meaning when any one of these switches get activated, output goes to ground, output is 0. Make sense? Right? So let's draw the circuit diagram. We have a pull-up resistor. We have 2 switches in parallel. If VA is 0, it remains open. If VB is 1 or 10 volts, it closes. Output goes to 0. Now, this is not 0 volts, okay? This is not 0 volts. This is logic 0 that I'm using. The actual voltage or current is something that you would have to calculate. Output is still 0. And why did I say we have to calculate? Because when it's on, there is a on resistance. So if you assume a on resistance of 400 ohms, it forms a voltage divider network with a 10 kilo ohm resistor. So if it forms a voltage divider with a 10 kilo ohm resistor, that on resistance of the switch is going to drop some voltage across it. And so you can calculate that voltage similar to the example shown on the previous slide. Okay. How about when both are on? What is the output? Output is still 0. But yes, you are saying you're on the right track. Nah, my ears are not that good. I mean, it's going to drop voltage, yes. But now both switches are in parallel. So you got two resistors, but instead of in series as in the previous example, in this example, they are in parallel. And so when both are on, both switches are on. So now you have R on and R on in parallel. Your output is 0, obviously, logic 0, I mean, but there's a drain resistance. So you need to find one single REQ. One single REQ means R on divided by 2, which would be approximately 200 ohms. And now you calculate the out voltage that drops across this 200 ohm resistance. It'll be very small. Previous one, I think, was 0.9 using 500 ohms. If you use 200 ohms and you calculate this, maybe around 0.3, 0.4 approximately, I would say. Does that make sense? All right, let's take a pause, quick, short pause. Let me know if you have questions. Okay, all right, good. What if you switch from a pull up to a pull down resistor? What do you think is going to happen? Without analyzing anything, when you had a pull up resistor, you had a what kind of gate? This one. Hold on. And this was the NAND gate. So instead of a pull up, you now use a pull down resistor. What kind of gate do you have? You all sure? All right, let's see. Okay, instead of let's sing, can you all explain it? All right, let's start with this. Both are in series, right? So what is the standard output? If both switches are open, what is the output? If both switches are open, output has a direct path to ground. So what happened to my, there you go. Output is 0. How about if one of the switches is open? What is my output? Still 0. And the only possible way output goes high is if both switches are closed. When both switches are closed, there's a pathway for it to connect to plus 10 volts. And hence, this is indeed an AND gate. That's an AND gate. Let me draw it. Sorry. You did it in what? Oh, you already did it in 145 lab. Oh, okay. Okay. I haven't reviewed the labs at all. So was the explanation provided? All right. This is VB equals 1, VA equals 0. This is if VB equals 0 and VA equals 1. The only way is when only way it goes high is and that's it. There you go. All right. Any other questions? Okay. All right. We'll end class here today. This was the last slide for today, and then we'll pick up on Wednesday. Okay.